Assalamu alaikum. My name is Malaika Rehman. I am from MS Chemistry, Batch 8, Semester 2. Today my topic of presentation is nickel titanium hafnium, which is represented as NiTiHf. First is its abstract. In its abstract, it tells us about that nickel titanium hafnium is a sharp memory alloy which works in advanced smart materials, works at high temperature, and used in the aerosols, automotive, medical, and energy systems, and many more. Its keywords are nickel titanium hafnium alloy, high temperature sharp memory alloy, Martenstic transformation, crystal structure, smart materials, and artificial intelligence. In its introduction, it tells us about what is sharp memory alloy. Materials that can remember their original shape, they formed at high temperature, recover shape when heated, and based on the phase transformation used in uh, actuators and smart devices. It tells us about nickel titanium works only when the temperature is below the 100 centimeters. Many industries need materials for high temperatures, which are in which nickel titanium added the hafnium, and new alloy is made, which is nickel titanium hafnium NiTiHf, and it can work on the temperature about 200 to the 300 degrees Celsius. Then, history of nickel titanium alloy. The development is closely linked to the historical evaluation of shape memory alloys. The shape memory effect was first observed in AuCd alloys, uh, gold and cadmium alloys. In 1930s, however, practical interest in the SMAs began after the discovery of nickel titanium, nitol, which is called nitol at US Naval Ordnance Laboratory in 1960s. NiTi rapidly gained attention due to its exceptional functional properties, but its limited operating temperatures. Range soon became apparent as industrial application expanded. During the 90s and during the 1980s and early 1990s, researchers began exploring ternary alloying strategies to raise the transformation temperature of nickel titanium, nitol, which is called as nitol. Early studies focuses on the elements such as Zr, zinc, hafnium, platinum, and gold. Among these, hafnium emerged as one of the most effective alloying elements due to its strong influence on lattice distortion and phase stability. Initial investigations demonstrated that partial substitution of titanium with hafnium significantly increased the Martenstic transformation temperature without completely suppressing the sharp memory effect. Then, in the mid-1990s, systematic experimental studies confirmed that increasing hafnium content, typically about 10 to 30% atomic percentage, um, uh, could raise transformation temperature well above the 200 degrees Celsius. This period marked the recognition of the nickel titanium hafnium as a distinct class of high temperature sharp memory alloys, rather than a simple modification of nickel titanium nitol. Researchers also observed that hafnium added increased lattice parameters, strengthened the atomic bonding, and enhanced the resistance to thermal degradation, although it has introduced challenges such as increased brittleness and processing difficulties. Then, from the early 20s onward, advancement in this processing techniques such as vacuum arc melting, powder metallurgy, rapid solidification, and thin film deposition enabled better compositional control and microstructure refinement of nickel titanium hafnium alloys. Then, heat temperature strategies including solution treatment and aging were developed to optimize the precipitate formation and improve the functional fatigue life. These developments significantly enhance the reliability and repeatability of nickel titanium hafnium alloy under the cyclic thermal and mechanical loading. In the recent years, researchers on this alloy has expanded toward thin films, micro electromechanical systems, which is abbreviated as MEMS, and additive manufacturing, driven by the demand for compact, high temperature actuators and sensors. The alloy has also gained attention for its potential role in the aerospace morphing structures, adaptive engine components, and smart system energy systems. Then, and modern research focuses on improving ductility, reducing hysteresis, enhancing cyclic stability, and integrating nickel titanium hafnium alloys with intelligent control systems. Then, the historical evaluation of nickel titanium hafnium alloy reflects a transition from basic alloy development to advanced functional material design, positioning it as a key material for the next generation high temperature smart applications. Then, its composition and the chemical formula of nickel titanium hafnium. Nickel titanium hafnium is basically a mixture of three alloys, which are nickel, titanium, and hafnium. Its chemical composition is hafnium content is about 5 to 30%, and nickel is nearly about 50% for phase stability, and it controls the compositional properties. Its general formula is nickel 50, Ti 50 minus X, and hafnium is X, atomic percentage. Then elemental composition and role of each element. First, role of nickel. It stabilizes the austenite phase, controls the transformational temperature. Small changes occur due to the big effect and important for reversibility of the material, and then affect the hysteresis behavior. Then the role of titanium, in which basic element of shape memory effect. It is a base memory of shape memory effect, enables the martensic transformation, provides corrosion resistance, and then works with nickel to form the B2 structure. Then hafnium, which is the third one atom. Its role is it replaces the titanium atom. Then it has a large atomic radius, enhances the atomic bonding strength, significantly raises the transformation temperature, and then improves the thermal stability of the lattice. Then its atomic weight and atomic and weight percentage composition. First, nickel titanium alloys are generally designed and reported in atomic percentage due to the nature of phase transformation and crystallographic considerations. However, because hafnium has a much higher atomicness than the titanium, its addition significantly increases the weight percentage. For example, हमने एक alloy लिया है with a composition of nickel 50, titanium 35, and hafnium, which is about 15, corresponds to a much higher HF content in weight percentage, often exceeding the 40% weight. This affects the density, melting behavior, and processing requirements, making the vacuum-based melting techniques essential, which are essential for the alloy fabrication. Then next heading is solubility and phase transformation, in which hafnium exhibits a high solid solubility in the lattice due to its chemical similarity to titanium. In well-processed nickel-titanium hafnium alloys, hafnium atoms occupy titanium lattice site without disrupting the fundamental B2 crystal lattice, in which at high uh, hafnium concentration or under improper heat treatment conditions, secondary phases such as hafnium-rich intermetallic may form, which can adversely affect the shape of memory performance. To avoid the unwanted phase formation, we use the strict control of composition, homogenization, heat treatment, and cooling rates are required. Optimized compositions ensures a single-phase B2 austenitic structure at high temperature and a fully reversible Martin-stick transformation upon the cooling. Then, crystal lattice of nickel-titanium hafnium alloys, in which we discuss the hafnium atoms are larger than the titanium atoms, in which the lattice structure expanded, which increases the internal stress, and then the Martin uh, Martin site becomes more stable, which forms the transformation occur at high temperature, and then in which the substitution of hafnium occurs with the titanium and the lattice expanded that introduces the internal strain and enhances the stability of Martin stick phase. At low at low temperatures, the alloy transforms from the B2 phase to the B19 structure, although in some composition, an intermediate orthorhombic B19 phase may also be appear. The exact structure depends on the hafnium content, nickel concentration, and heat treatment conditions. Here is the diagram of B12 formation to the B19 formation, phase transformation, and orthorhombic structure of B19 phase. Then next is Martin stick phase characteristic. In this, it is a low temperature phase in which B19 monoclinic structures are used to form the crystal distortion, to create the crystal distortion. In the B19 phase, the lattice undergoes shear and shuffle distortion relative to the parent B2 phase. These distortions produces a multiple variants which accommodate the deformation through twinning rather than slip. The presence of hafnium increases the lattice distortion, resulting in the enhanced phase stability at increased temperature, and this increase in the distortion is one of the primary reasons for the higher transformation temperature observed in the nickel titanium hafnium alloys compared to the conventional nitol. Then next is phase transformation mechanism. In this, alloy is a thermoelastic transformation which is reversible and diffusion-less. Upon cooling from the high temperature, the alloy undergoes a transformation from B to austenite to the martensite when the temperature reaches the start temperature. As the cooling continues, the formation progresses until completion at the final temperature, which is represented as MF. In this, upon heating, the reverse transformation occurs and transform back into the martensite lattice, transform into the austenite between the austenite start and austenite finish temperatures. This reversible transformation is responsible for the shape memory effect, and it causes the deformation which is recovered during the heating as the alloy return to the austenite phase. Implementation of the hafnium raises all transformation temperatures, which is MF. MF, the start temperatures of martensite or final temperature, austenite start temperature, and austenite final temperature by stabilizing the phases and increases the energy barrier, which is required for reverse transformation. Next is the diagram of the thermoelastic Martensite phase transformation in the nickel titanium hafnium alloys. It is the as the temperature जैसे जैसे cooling होगी then next is transformation hysteresis, and this the difference between the heating and the cooling processes occur. It tells us about that the nickel titanium hafnium is larger than the nickel titanium nitol due to the strong bonding, which increases the stability and also slightly reduces the efficiency. Then next is effect of composition on transformation behavior. The transformation mechanism is highly sensitive to the alloy composition. Increasing hafnium content generally increases transformation temperature and stabilizes the martensite phase. But excessive hafnium may suppress the reversibility or promote the secondary phase formation. Similarly, slight deviation in the nickel content can significantly alter the transformation temperature and phase stability, which is the process of B2 to B19 transformation. And this optimized composition and heat treatments are therefore essential to achieve a fully reversible process of B2 to B19 transformation with stable functional performance. Next is comparison of nickel titanium hafnium with the nickel titanium ZR. It provides the nickel titanium hafnium has better stability than the nickel titanium ZR zirconium. It causes the more lattice distortion, and this higher transformation temperature occurs, and then it creates the better cyclic performance. It is more reliable at the high temperature. As a result, its functional properties are retained. Next is comparison of nickel titanium hafnium with nickel titanium platinum NiTiPd. In this, nickel titanium platinum has a very high cost. Platinum significantly raises the transformation temperature of NiTi. Platinum has a high density, as compared to hafnium is lighter than platinum. So nickel titanium hafnium offers a better strength to weight ratio. In addition, platinum is a precious metal, which is very expensive than the nickel titanium hafnium. Nickel titanium hafnium is a cost-effective or affordable, and then therefore nickel titanium provides a cost-effective and lightweight alternative for high-temperature SMA, which is shape memory alloy applications. Next is fabrication methods of nickel titanium hafnium alloys. In this overview, the fabrication of the nickel titanium hafnium alloy is more challenging than that of conventional alloy due to high temperature, larger atomic mass, and strong reactivity of hafnium. Precise compositional control and prevention of contamination are essential, as small variations in the nickel and the hafnium content can significantly influence the phase formation behavior and functional properties. Therefore, nickel alloys are typically fabricated using the advanced melting and processing technique under the controlled atmosphere. Next one is the diagram of vacuum arc melting. Next step is induction melting. In this process, vacuum arc melting is basically it is a melting under vacuum or argon, prevents the oxidation. Multiple remelting for uniformity occurs and it is a common laboratory method. Next step is induction melting. In this process, we use the electromagnetic heating, uniform temperature, and it creates a good mixing of metals at melting point, and it is suitable for large ingots. Then the then it is a process of how the nickel titanium hafnium is melt in the metal conversion goes in the metal alloy furnace and then goes to the large and nickel titanium hafnium ingot. Then the next step is powder metallurgy. In this process, we use the metals in powdered form, which is in a fine grain structure. It reduces the segregation and it is suitable for complex shapes. Here is a complete process of the powder metallurgy, how the nickel titanium or hafnium goes to mixing and blending, then compaction occurs, then sintering, and then the temperature then goes to the furnace and then blended powder obtained. Then also write its advantages is it reduces the segregation, fine grain size, and near net shape compatibility. And its challenges are powder oxidation, high cost of hafnium. Next is thermomechanical processing. In this, solution treatment removes secondary phases, aging improves the strength and improves transformation stability, essential for good performance. Here is a complete process of the thermogen process. Heat, temperature, and homogenization. In this solution treatment at high temperature is applied to dissolve the secondary phases and they homogenizes the distribution of hafnium. And then aging treatment are employed to promote the formation of the fine precipitates that enhances the high temperature strength and cyclic stability. Then the next step is thin film and advanced fabrication techniques. In this, thin film techniques are used such as magnetron, sputtering, and plus laser deposition. These methods allow precise control of composition and thickness. And then the second one is additive manufacturing techniques such as laser powders, fusion bedding have been explored for nickel titanium alloys, although still under development process. It's a process how the solution treatment goes to the aging treatment and then नीचे एक डायग्राम बताई गई है जिसमें उन्होंने हमें बताया बिफोर ट्रीटमेंट उसका क्या स्ट्रक्चर होता है होमोजेनाइज होके एंड देन फाइन प्रेसिपिटेट्स. Then the next step is its properties. Overview में है nickel titanium hafnium alloys exhibit a unique composition of functional, mechanical, thermal, and physical properties, and these properties make the nickel titanium hafnium alloy particularly suitable for applications which require the thermal stability, high transformation, temperature, and reliable equations under extreme conditions. Such its property is shear memory and superelastic properties. It will announce the shear memory effect, which enables the material to recover the large inelastic strain upon heating after deformation in the martensitic state. This behavior originates from a reversible solid phase transformation between the low temperature and the high temperature austenite phase. At the suitable composition, the alloy recover the strain about 3 to 6%, which is slightly lower than the binary nitol, but significantly higher than many other high temperature smart memory alloys. It reduces the stiffness of the lattice and which is a main cause of addition of hafnium. The transformation temperature characteristic. One of the most important property of alloy, which alloys in the elevated Martin-Stick transformation temperature. While conventional nitol allows typical transformation below 100 degrees Celsius, nitol alloys can exhibit the transformation temperature exceeding 200 to the 300 degrees Celsius, depending upon the concentration of the hafnium which are used in the material and then the heat treatment. The transformation temperature increases almost linearly with increasing hafnium content. Hafnium stabilizes the structure, and also it is ideal for the high temperature, actuators, and thermal sensing applications. Then its mechanical properties. In mechanical properties, it tells us about the high strength, high elastic modulus, and also the creep resistance, which is better, and it reduces the ductility of the hafnium it reduces the ductility at when the content of the hafnium increases. Then the second step is thermal stability and creep resistance. In this, it works on the 200 to the 300 degrees Celsius, which we read on the previous slide. It stabilizes the thermal cycling, less degradation of nitol occur, and it is suitable for the long-term use. Then creep resistance and nickel titanium alloy enhances the creep resistance due to the high melting point and strong atomic bonding of hafnium. Then the second one is functional fatigue behavior. It refers to the degradation of shape memory performance in the repeated thermal and mechanical cycling. It allows the improved high temperature functional fatigue resistance, which is compared to nitol alloys operating beyond their safe temperature range. The functional fatigue life of nickel titanium hafnium alloy is influenced by the factors such as composition, microstructures, precipitate formation, and applied stress. Then corrosion and oxidation. In this, nickel titanium alloys inhibits a good corrosion resistance, particularly in neutral and mildly aggressive environment. At high temperature, oxidation becomes a concern due to affinity of titanium and hafnium for oxygen. It needs coating for protection, and it is important in the aerosol use. Next one is physical properties of nickel titanium hafnium. In this, it compares the nickel titanium hafnium with nitol due to the high atomic mass of hafnium. The alloy exhibits a higher thermal expansion coefficient, and it increases the electrical resistivity. The physical property changes must be considered due to component design in the aerosol and precise actuator application. Next is the application of nickel titanium hafnium alloy, in which first one is aerosol application. In this application, high temperature actuators are used for morphine the wings, and it is used in the engine components, and it controls the vibrations. And the second is automotive application. In this, high temperature valves, sensors, and actuators are used, which are essential for the thermal switches and turbocharger actuators, and then it controls the emission of the system. Next one is the medical application. Next one is the medical application, in which we studied First one is cardiovascular devices. In these devices, transformation stunts are made. These are tiny mesh tubes used to open the blocked arteries by because the nickel titanium has high transformation stability, um, which is used for the which is used to open the program shape once it reaches in the warm environment of the heart. And and the then in the orthopedics, used in the bones and the joints, nickel titanium is used for implants. The need of mimic the flexibility of human bone staples. Doctors use these to hold the fracture bones together, and the staple is inserted in a loose shape. Once it warms up to the body, it naturally tightens and pulling the bone fragments together to speed up the heating. Next is spinal spacers. These help maintain the gap between the vertebrae. It increases the stability. It gives the stability to handle the high stress and shows the spacer, and it doesn't collapse under the weight of the patient's body. Next, next is the energy and power systems. In this, thermal switches are made, smart valves are used, and adaptive flow control devices in the power plants and energy harvesting systems are made. Then, the ability of the nickel titanium alloy to convert the thermal energy into the mechanical motion make them attractive for waste heat recovery systems. Next one is micro electromechanical system, MEMS. In this, with the advancement in thin film fabrication techniques, alloys are increasing use in micro electromechanical systems. High temperature micro actuators, micro sensors, and micro valves fabricated from the nickel titanium hafnium, and which operate in the harsh environment. And second one is then compared to the traditional micro electromechanical system materials, and to the nickel titanium hafnium alloys, which provide the large equation strains, compact size, and autonomous thermal response, making them ideal for miniaturized the smart systems. Next application is industrial and smart actuator system. In this, while industrial smart actuators are that require the stable operation under repeated thermal cycling. These include the automotive safety devices, temperature control switches, and adaptive mechanical coupling. Research and advancement in training application. In this, in academic and industrial research, as modern materials for studying the high temperature, phase transformation, functional fatigue, and smart material behavior. They also serve as a benchmark material for the development of the next generation. Next are the advantages of the nickel titanium hafnium and limitations. In the advantages, first one is its advantages. It attains the high temperature, high transformation temperature. It is excellent for thermal stability. It gives the high strength, and it gives good creep resistance and reliable for smart behavior. Its limitations are, first one is it has low ductility. Processing of fabrication is very low. It has high density. It causes the oxidation issues and large hysteresis. Then next one is future scope of nickel titanium hafnium alloys. In this, it improves the ductility, better fatigue life, and then it creates the thin films for amines, and advancement in the additive manufacturing, and also adaptive for the and also for the smart adaptive systems. Then the role of AI in the nickel titanium hafnium alloy development. And the artificial intelligence play a transformative role in the future development by predicting the properties, optimizing the composition, reduces the experiments, and improve the manufacturing, and also enable the intelligent materials. In this, machine learning algorithm can also be used to predict the transformation temperatures, mechanical properties, and functional fatigue behavior based on alloy composition and heat temperature treatment parameters. It also enables the rapid screening of nickel titanium hafnium composition, which are specific for the high temperature applications. In manufacturing, AI can support the processing of optimization and quality control, particularly in the advanced fabrication techniques such as additive manufacturing and thin film deposition. In the real-time data analysis and predictive control systems can help the minimize defects and control case formation and ensures the producible shape memory behavior. Next one is smart systems and AI integrated application. In these applications, AI-driven feedback mechanism can be integrated with the nickel titanium hafnium actuators to enable the self-adjusting, self-monitoring, and self-energy efficient smart structures. In the long-term use, nickel titanium alloy may become a key material in AI-enabled smart materials platforms where materials can autonomously respond to environmental changes and also predict the failure and optimize their own performance during the services. It's then the conclusion in this. It is nickel titanium hafnium is an advanced high temperature smart memory alloy. Hafnium improves the temperature and stability, and it is also suitable for the extreme conditions, enhances the thermal stability and improve the high temperature mechanical performances, and it is helpful for processing the challenges, and it has a strong future potential. Thank you so much.